Okay, hi everybody. Welcome. So I'm going to introduce our speaker. I'm Daniel Cohen, Professor of Sociology. Mathew Hauer is an assistant professor of sociology at Florida State University, where he studies the impacts of climate change on society. I would say that Matt's one of the country's rising stars in the social science of climate change. He's published very impactful articles in Nature, Climate Change, Population and Environment, PLOS One, Justice Quarterly, and elsewhere. His recent research is focused on how migration induced by sea level rise could reshape U.S. population distribution. And his findings from a few years ago that up to 13 million Americans could be displaced by sea level rise has really defined the debate on climate change migration in the U.S. And that research was featured in places like the New York Times, National Geographic, Time Magazine, The Guardian, Popular Science, USA Today, and other places. And he's got even more frightening and sophisticated research coming down the pipeline. So I can assure you there will be even more coverage of the blockbuster research he'll be telling us about now, and other research he's doing. Research with partnerships include the Union of Concerned Scientists and Climate Central. Before coming to Florida State, Matt spent 8 years directing the applied demography program at the University of Georgia, where he provided valuable demographic research to local, state, and federal governments. So extremely thrilled to have Matt. Just give him a warm welcome.
Thanks. Thank you. Thank you. Thanks for having me. It's really great to be here. Penn's got such a great pop center, so it's just really wonderful to be here. So I'm going to talk about my work on sea level rise and migration, and I'm going to talk about work that I've already published, and I'm going to also talk about hopefully forthcoming work that I'm moving into relatively rapidly. So I don't think this is necessarily a controversial statement that climate change is one of the most pressing issues in the 21st century that we face. But what I'm really going to argue is that sea level rise is eventually going to force millions of people from coastal areas in the United States and cause essentially a reordering of where people live in this country. I'm going to focus on the U.S., but some of this is very applicable elsewhere globally. It's just the data in the U.S. is really good when it comes to doing this type of work. So this is really unique when we think about sea level rise and migration for really three reasons. So as I'll show, this migration that's anticipated is going to be larger than the Great Migration of African Americans out of the rural South and into the industrial North in California. So it's going to be as large or larger just from sea level rise alone. We largely know that this is going to happen too. The science on this is pretty solid. It's a bit different in thinking about something like the Great Migration, where you have societal change. This is a bit more. If we don't actually do something about sea level rise, we're talking about the conversion of habitable land into uninhabitable water. And then migration scholarship has really come a really long way in the last 30 years or so, where we actually finally have data, where we can do some modeling on this, the theories around where people might go, and so on. It's just so much more equipped today. So it's sort of sitting on a unique place in history to actually begin to kind of do this type of scholarship. So this is what I'm going to really talk about today. I'm going to focus on four questions. The first two are ones that I've already published on, which is how many people could be displaced by sea level rise. When I started doing this, there was no high-end number. We didn't really know. And then displacement and migration implies a destination. So it seems very natural to then ask, if people are displaced by sea level rise, where are they likely to go? Where are their destinations? And then all the work up until then has largely been, I like to describe it as stick figure people. They're ageless, genderless, raceless. And so I'm starting to fill in the demographics of who these people might be. And then also when are these impacts going to occur? And then depending on the time, because I know it's hard to keep people engaged for longer than 45 minutes, what we can actually do about it. So depending on time, I'll talk a bit relatively briefly about adaptation. So if you need a real quick primer on sea level rise, this is sea level rise in a single slide. Since 1900, sea levels have risen by about 8 inches or so or about 0.2 meters. And by the end of the century, they're expected to be upwards of 2+ meters by 2100. It doesn't end at 2100. There's multi-centennial projections that go out another 2,000 years. But they show upwards of 7 meters as well by 2300. The figure you see here is just NOAA's last technical report from 2017, where they're showing the suggested curves. That dark red line is about 8.5 feet right now by 2100. The previous technical report from NOAA from 2014 had the highest high being 6 feet. The lowest low, that dark blue, has remained relatively unchanged between reports as new physical science starts to come in. So all that's really happened when it comes to sea level rise curves is that the probability for higher amounts of sea level rise is increasingly likely, whereas the probability of low-end sea level rise has not really changed a whole lot. So I'm going to model, because some of this work originated in 2013 and 2014, I'm really going to talk pretty much exclusively about 6 feet of sea level rise, as opposed to 8.5 or in some cases 10 feet. So in order to try and model this migration, you really need to do two things. I think of it like plumbing, as a plumbing analogy. We have to figure out the pipes that it's going to take people to different places. And then we also have to figure out how much water is actually in the piping, which would be the people. So that's the magnitude of flows, is how much water is moving through the pipes. And the migration framework is the network by which people are actually going to move. So I'll talk about those two separately and in chronological order, starting with the magnitude of flows. So we have how many people are then going to flow to which destinations. So to figure out how many people are at risk to sea level rise is a relatively simple calculation. The first one that I could find in the literature was from 1980. A group of atmospheric chemists published one showing really simple, right? You have 3 feet of sea level rise, so everybody who lives under 3 feet of elevation would therefore be at risk and would have to be displaced. But there's a big temporal mismatch in doing that because sea level rise is not today, it's a future hazard. So this is California's population in the 20th century. And so if we were to look at 2015 today, we'd say how many people are at risk. We might say 37 million. If we had started the same period in 1915, we would have used 4 million people. So we'd miss the massive amount of growth that California underwent in the 20th century if we were positioned to do the same analysis 100 years ago that we would be doing today. So we have to account for ongoing population change in a lot of coastal communities in order to actually be able to answer this kind of question. Otherwise, we end up potentially underestimating how many people would actually be at risk. And the second would be a spatial mismatch. And again, this goes back to being uniquely positioned today to actually do this. The geophysical modeling that the physical scientists are using is increasingly sophisticated and increasingly detailed. I really like this figure because it really shows how well or how downscaled the modeling has been in the last few years. The red square is just a 100-meter grid cell that the physical scientists were using upwards of 10 years ago. Today, you can get 10-meter grid cell resolution, which is basically home plate to the pitching mound. And in some cases, you can get 3-meter resolution, which is really, really tiny. Now, those are far smaller than any census unit of analysis that we have. But it's important because not every county is actually at risk. This is just 4 different areas. We have San Francisco Bay Area in the top left, Washington, D.C., Boston in the bottom left, and in the bottom right would be Charleston. And how many, those are census block group boundaries mapped onto 3 feet and 6 feet of sea level rise. So there's not a single county where you see everyone being underwater. And some of the prior work in this area was using county boundaries to do this analysis. And it's really important to get as close to a spatial joint as you possibly can, where the hazard actually maps onto the actual population characteristics. So what I did is I created small area population projections for every single coastal county in the United States. This is relatively difficult to do because small area boundaries change between every census. This is the modifiable aerial unit problem. And this a guy at Wisconsin had published this really nifty method to standardize block group boundaries historically back to 1940 using the year structure built question. But it required the growth to either always be up or always be down. And if you relax that, you end up with differential growth patterns. So this is a single county with different block groups, and they all have different growth patterns that they're exhibiting. The decline one would be a central city a block group where the number of housing units has declined. And so this is real easy to put into just a simple time series extrapolation where we're borrowing 80 years worth of time to then go forward to see how these growth patterns go out into the future, which gives us small areas that are then, so our spatial mismatch is minimized, and it gives us a population projection, which means that our temporal mismatch is minimized as well. And so layering these two together, calculating how many people would be residing under certain elevation thresholds. In this case, it would be 3 feet and 6 feet of sea level rise. So this is the big finding. If you look at the growth, the blue line, it would be a 6-foot curve, or 1.8 meters by 2100, which would lead to about 13 million people that would be at risk of sea level rise. And the orange curve would be if we have 3 feet of sea level rise, where you're looking at just over 4 million people. This highly concentrated in the southeast, in particular, the Gulf, what is essentially Tampa south all the way up through to Jacksonville in Florida, in Louisiana, but there's a lot of other areas as well that have high concentrations of people that are at risk, specifically in the San Francisco Bay Area and in parts of New York as well. There's not a differentiation as well between the different the sea level rise curves until after about 2060, when sea level rise really starts to accelerate towards the end of the century. And the difference between the current numbers in those areas and the projected is essentially double. So there'll be twice as many people in these areas in 2100 than there would be today. You can also see that Florida is 6 million of the 13 million that would be at risk of 6 feet of sea level rise. So it's super concentrated. Louisiana would be the second most at-risk state numerically, and it's much more. It has a much smaller population than California, and yet California, it still has more people that would be at risk compared to California. Sure. Yeah. Absolutely.
So when you make these population projections, do you think they set? Because I think that changing climate will also influence where people are going to be. So that what the past projection of their population growth is unlikely to be the same into the future, given that people are shocked.
Yes. Yeah.
So is that sort of modeled into this?
Uh,
That sort of feedback loop from changes in climate to the population size?
Yeah, we have a one-way. It's only one way, though. So we don't end up double counting people. We allow them to move out of an area, which changes the curve in the risk profile. But it's not. It doesn't change anything else about. They don't integrate yet. They're not integrated. That's one of the areas where I want to move to as well as building a better projection model than just an extrapolation, right? Which I've got to that point, just not yet on there. The curves are all really different. This was unpublished. When we did this originally, we had 1 foot of sea level rise as well, and our reviewer didn't like it, so we threw it out. But this would be Charleston, Miami-Dade, San Mateo, and Monroe County, Florida. And this is kind of getting to your question. In the case of Charleston, each curve is rather distinct in this really nice fan pattern in terms of 1, 3, and 6 feet of sea level rise. In Miami-Dade, on the other hand, the difference between 3 feet and 6 feet of sea level rise is essentially an order of magnitude. So 3 feet is manageable in Miami. It's not so manageable with 6 feet. In San Diego, in San Mateo County, the curves start to overlap. So if you were, for instance, in San Mateo, it didn't really matter if you're going to plan for 3 feet or 6 feet. And then in Monroe County, if you look at the blue curve, you start to see it flatten out. And that's because essentially Monroe County runs out of people to be displaced by 2100 with 6 feet of sea level rise. So the curve starts to get flat. We published like a lot of data and a massive amount of extended results. And I just want to highlight a couple. These are the counties that all have over 2/3 of their population would be underwater with 6 feet of sea level rise. And some of them are really tiny. In the case of Tyrell, Monroe, and Hyde County, those are the Tyrell and Hyde are Outer Banks. Monroe's the Florida Keys. You're looking at over 80% of the population that would be displaced. And it's hard to imagine any kind of adaptation that would be strong enough to prevent that level of displacement in those areas, especially in Tyrell and Hyde, where they're already very rural. Broward and Miami-Dade, which are much lower on the list, have a lower relative risk, but their numeric risk is really, really high, where they account alone for 1.9 million and 1.5 million people that would be at risk of displacement. So they're a quarter of the people that would be at risk of displacement from sea level rise in the U.S. are located in Miami-Dade or Broward County. So it's a super localized effect. There's 6 counties with over 100,000 people that would be impacted with just 3 feet of sea level rise. And then there's another 31 counties with 6 feet. Again, Miami-Dade and Broward were 1 in 4 persons that would be impacted. And then we kind of put this in at the end of the manuscript about managed retreat, where there's still a big discussion around how we could actually buy people out. And when this paper came out in 2016, the best estimates for the managed retreats that were underway in the United States at the time were about $1 million a resident. And so the 13 million, the high end would be 15. So 15 million times $1 million is $15 trillion if we were to buy everybody out. Now, since that paper came out, the cost estimates were a bit more robust. And so they're really more like $200,000 per person for the managed retreats. So instead of 15 trillion, it's only $3 trillion. And then I got a lot of pushback around growth patterns where people were saying, well, they're not going to keep growing like that. I say, fine, you could just use the current populations if we were to buy everybody out, which is about half as much. So instead of 3 trillion, it's 1.5 trillion. So essentially, any way you slice it, if we were to do a managed retreat for everyone that would be at risk of displacement in the U.S., it would be a lot of money. Very, very expensive to do. So this tells us, oh yeah, and the geography is really weird. Oh, so the geography is real weird. This is Miami-Dade and Broward County. This would be 6 feet of sea level rise. And if you look, everything that is the dark blue is areas that would be flooding out with 6 feet. And I want to highlight Weston, the city of Weston, Florida, which is 17 miles from the coast. And so a lot of times when this sort of physical hazard manifests, it doesn't always follow a nice sort of, well, I'm right next to the coast, therefore I'm going to flood. In the case of South Florida, you can be pretty far from the ocean and still be at very elevated risk of sea level rise. The green area is areas that are low-lying and would be at risk of flooding because of a rain event or something similar. So where will people go? So migration, like we know a lot more about migration decision-making over the last 30 years. And so where people actually tend to move is largely driven by established social networks and social capital. So people tend to move where you can have enhanced social capital. And these sort of environmental stressors like climate change, they operate independently of environmental stressors, act independently of the pull factor. So the push factors are independent of the pull. So a place like Chicago is still going to be attractive because it's being unaffected by sea level rise. So climate migrants are likely to constitute enhanced or extra normal outmigration, especially as it relates to what we would call a slow onset environmental change, something like sea level rise as opposed to a fast onset, like a hurricane. And I really like this approach that Richard Black published a few years ago from the Foresight Report, which shows how all the different sort of factors that go into making why somebody might migrate. It's not just sea level rise. It's sort of these different environmental factors and political and economic and demographic and so on. There's intervening obstacles and facilitators as well to migration too. I have no personal desire to model all of this because this would be a really complicated model that might not tell us a whole lot about behaviors. Instead, these are the same reasons why anybody migrates generally. And so we can use pre-existing migration network information to figure out where people are likely to actually migrate to. And so I used data from the IRS county-to-county migration flows for 1990 to 2013. I would have used a later time, but they changed the time series, making it rather difficult to rectify. And then I took all these dyadic pairs for each county to each county and just used a time series model. It's a dynamic linear model called an unobserved component model to forecast where people might go so the migration system can change over time. So it's not sort of locked in. It allows pairs to wax and wane. And here's some sample networks right here for Eagle County, Colorado, a personal favorite, Dougherty County, Georgia, which is the city of Albany, and Assumption Parish, Louisiana. So if somebody were to say, well, why would anybody move to Buffalo, New York? I think that's Buffalo. I don't know why any individual would, just that this is actually where people moved in 2013 from Assumption Parish. Some people did move to, is that Buffalo? Yeah, or is that Syracuse? It's Buffalo. So people did move to Buffalo. Or why would anybody move from Miami to Albany? I don't know. There's a lot of reasons why, but somebody did inside the IRS data.
What's the difference between the IRS and the census data? Because I know that since they also published their report that includes country-to-country migration and even at a more aggregated level.
Yeah, so the IRS data is a really nice universe. It's 95 to 98% of the tax filing universe and their dependents inside the data on an annual basis. So it's a huge administrative sample, if you will. It's almost everybody in the U.S. It's 88% of all households fall within the IRS data, but it has structural exclusions around specifically college students, very poor, and the elderly, among other populations. So it's really good in a lot of cases, but it has strong biases in its sample or in its output. The census data doesn't have that, but it's sample based, and so now you only have 2.5 million households. So the uncertainties inside of it are much wider, and the time series isn't as good that they publish on for the data. They only started publishing the time series starting in 2000. With the first 5 year, which would be 2009, the 05 to 09 ACS. There's some stuff in the decennial for Census 2000, but it's a 5-year window. The window, right, they ask is, where did you live 5 years ago? In the ACS, it's where did you live 1 year ago? So you have differences in sort of measurement as well. So those are, you don't have as much time slices with the census data versus the IRS. You have a smaller sample compared to the IRS, but you have something that's more representative of right, a full population in the census data versus the IRS.
But this is based on their W-2 tax return. What if someone has multiple residences?
Yeah, so that's one of the other weaknesses in using the IRS data. Yeah, and that was actually what caused the structural break in their time series starting in 2013. They started allowing households to not migrate together. They were allowed to disentangle. Yeah, so college students are a part of the bias in the samples or in the universe too. Mm-hmm. Yeah, so I mean that's how they do it. They match it up. So if you change residences on your IRS form, then you're considered a migrant. The census has the same problem if you have multiple residences because it's a usual place of residence question.
Okay, well, so I mean just as someone own a home very close to the coastal area, but they don't live there, they just own it, and they file their taxes for avoiding paying extra taxes, so they just move that address. So the population under risk is different from when you use it from the address.
Yes, that could definitely happen. I don't know the extent to it that it does though.
Have you thought about doing a little data moving by socioeconomic, by income, to see rich people? Because also the question that this is going to push into migration, people who do not normally migrate. So usually you look at terms of migration, this could be college educated, high income, so it will give us a sense about what's going to happen when everybody migrate. The low income are going to different places, and something about that.
I have, but it's not inside the IRS data at all.
Oh, you don't have.
I don't have the access to that data. Yeah, they give you the aggregate income. So right, the aggregate income of individuals moving from A to B, but so you can infer a per capita amount, but you wouldn't know.
If we were going to the census centers, I think you could get individual records, but but I don't know.
Yeah. I want to move into there, especially when I start doing things besides just right. Everyone is just a stick figure, which is where they're at in this model right here. It's just a stick figure.
I wonder if these migration patterns that will take you down and migration as a response to sea level rise, the past migration patterns eventually ignored it. Going forward, so we'll take this into account, and so then we expect that future migration is very different from the one we expect.
Yeah, so I have when I get to there's sort of out of order, but I have a paper that's coming out in June where we show that people tend to move after an environmental event that overwhelms and everyone moves. So when everyone moves, they move to the exact same destinations that they moved to beforehand because they're leveraging social networks in their decision-making process. So here, so the past migration patterns are very illustrative of where people actually move to because it's already embedded in the system that we observe. So people are already leveraging their social networks in their migration decision-making. And in the case of even a rapid onset or a slow onset, they also leverage it too. Mm-hmm. Yeah, it could be because they're not. I'm not pairing these, right? So I'm at the population level, so they're not paired. So I don't know anything about the destination similarities between people. But these migration patterns are remarkably stable in the U.S. There's very little change year to year, and there's very little change after a decade. It's still a really small change, but it's the UCMs are projecting those forward, so it's a sort of change, right? The migration patterns do. You can capture some of that waxing and waning. So in the results, Austin pops up a lot. There was a paper that just came out a week ago where they didn't have Austin as a top destination because they took the current migration pattern and they locked it in for a century. So there was no change in the migration system. And so in their case, they had Dallas as a top receiving community because Dallas is right now, but it might not be in the future. So I'm trying to capture that instability or change in the system.
We hold the rest of the questions until the end. I know Matt has a ton to get through.
Oh, sure.
We only go until 1.
Oh, yeah. So here's a figure. This is every state to every state. This is a chord diagram or a bilateral flow. It's arranged clockwise based around the size of the inflow. So Florida in the top right is the largest inflow of people that are migrating because of sea level rise. And then it's colored based on the top 10 sending areas, the top 10 outflows. So just to show, right, here would be people moving from Florida into Texas, that band right there. All of the top 10 sending states are also the top 10 receiving states, except for one, which is Georgia, which is a top 10 receiving but not a top 10 sending state. And if you notice, most of these actually have migration is going within the state. So this very large band of people migrating from Florida to other parts of Florida, which is exactly what you would expect from the literature. The literature suggests almost all climate migration is expected to be internal. And if you treat states are very similar in a lot of ways to internal countries in terms of their population sizes. So it makes a lot of sense that people would move short distances within their state. So I didn't program that in. It's just sort of the way what the results kind of came what the literature is suggesting. This is kind of complicated. So if we were to just aggregate, Texas would gain about 1.5 million residents. So the net change, right, in versus out. Florida, on the other hand, would lose 2.5 million residents. So, of the 6 million people that would be on the move, only 2.5 would actually be, going elsewhere from the state, or they'd only lose 2.5 million people. If you think about destinations, these are the destinations for migrants. Essentially, every state receives some group of people. On the left is counties, and on the right is MSAs. And so you can see almost every area that actually will gain people in the rest of the U.S. But places like Orlando, Austin, D.C., Atlanta, Denver are all major receivers. To put these numbers in perspective, I also modeled, well, what happens if these communities adapt to sea level rise? So that way, right, it's not like they're powerless in these communities. They can actually do something. And so without any kind of adaptation, the fringes of the distribution, the ends of it don't really change a whole lot. Austin, Orlando, and Atlanta still remain the top destinations. Miami and New Orleans, they still remain in the top senders as well. They still lose the most amount of people. But everyone sort of in the middle of the distribution can change pretty significantly, and signs can shift as well. So New York goes from being negative to positive, for instance, as being in terms of its change. Most of that's internal within the MSA. So yeah, Miami still loses 2 million residents. So millions of people are exposed to sea level rise by the end of the century. It's not just a coastal hazard, but it has sort of a second order effects elsewhere. If we think about migration, there has to be a destination. You can't just migrate to nowhere. And that this is essentially going to really alter the U.S. population distribution into the future. So those are how many and where. So I started moving into who is at risk to actually flesh this out a bit better and to have a better population model. And so this is really, really simple to do. County level population projections in the US are really difficult in a cohort component because we don't have enough data to actually run a cohort component model. I mean, we do, but you don't really have access to it publicly. There's only, there's 500 counties in the United States have fertility data that's published by the NCHS. So you can't actually get your fertility input for a cohort component. But if you think about cohort change ratios, which are a simplified version, and then cohort change differences, which is the linear version of a cohort change ratio, it allows us to only use population components, the distribution, to actually project the population. So they're really easy. If we have 100 0-year-olds in 2010, and then 5 years later we have 120 5-year-olds, so we picked up 20. And a cohort change ratio, we just take the difference and multiply it out by the new population to get a projected of 108. A difference is just taking the difference. So 120 minus 100 gives us plus 20. So it's a linear growth as opposed to a decline. I use these to project out every county by age, by sex, and by race to 2100, and then controlled them to what's coming out of YASA with the shared socioeconomic pathways. So that way, the downscale county level population projections would not run the risk of being over projected or in the future, and would be able to be in concert with the SSPs for that literature. And so when you do this for the coast, right, so who occupies coastal communities in the US right now, if we look at 2020, which would be the closest to today that we have for the SSPs, the coastal US is largely white non-Hispanic. And I'm stuck with these categories because of NCHS, where just over 50% of the coastal US population is white non-Hispanic. But as the century goes on, the growth in our Black, Hispanic, and other, which is largely going to be Asian and multiracial, all grow, and our white non-Hispanic actually decreases. So, oh, that was supposed to disappear. Hang on, let me fix that. There we go. In which case, who actually resides in coastal communities is not a white non-Hispanic population, but largely going to be a plurality of non-white populations. So who's actually at risk in terms of race? If you were looking at it today, it's mainly a white non-Hispanic. By the end of the century, when impacts are particularly bad, it's largely non-white. It also has similar, we have an age effect that's really extreme too. In this pyramid, the red is the current populations in coastal counties in the US, and then the hollow bars are what it would be in 2100. So the aging effect here is really, really strong, where almost all growth that's going to happen is going to be over the age of 55 in many of these communities. So this has a really profound impact in terms of vulnerability and exposure. And because of sex differences in those age groups as well, it's largely elderly women in those age groups as opposed to elderly men. And so, right, so in terms of migration, this has a pretty strong role. This is a classic migration curve, right, the probability of migrating. In 2020, the US population was 33.5 with a median age. If we look at the median age at 47.5 for 2100 for the US, it's about a 10 percentage point drop in the probability of migrating. And for many of these coastal communities, the median age today versus in 2100 is pretty drastic. These are the 25 most impacted counties for sea level rise, and some of them become really, really old by the end of the century. In the case of Collier County, it would become one of the oldest counties in the US. Sumter County, Florida has the oldest median age right now, which is right around, I want to say 57. And so having a median age of 65 is considerably higher. So migration is adaptation. Maybe it's not an actual feasible strategy given this level of anticipated aging. And so there's a large discussion in the literature around trapped populations, but it's almost entirely economically trapped. But we might end up with demographically trapped populations too. And so I'm working to incorporate this into the migration model so that way, you know, I can actually change the propensities of migrating. And so, yeah, communities of color and the elderly would face intensified impacts by the end of the century. It's a brand, if we were to use current data, which is how a lot of these social vulnerability analyses are conducted, this would largely go undetected. You wouldn't see this effect. So it's going to be a new source of inequality that it transmits across time. And then when? So these are king tides, and most of these are from 2016 or later. On the one on the left, that's Brunswick, Georgia, because I was at the University of Georgia for 10 years, so I did a lot of work in coastal Georgia. That's Brunswick, Georgia. The one in the middle with the old man with his putting out his garbage bins, that's Tybee Island, Georgia, and the one on the bottom right is actually Miami. Yeah, so a king tide is the highest tide of the year. So you have, right, what drives the tides are where the sun and the moon are in relation to the earth. And so when they get on the same side together, they pull really hard, and so you get an extra normal tide. You get what they call the hat, which is a perfect acronym for it. It's the highest astronomical tide, so I really like how they called it that, the hat. And so these are the hats. These are the king tides. They happen twice a year in the spring and in the fall. These are fall king tides. And this is literally just a high tide. This is not a rain event. This is just a high tide. This is the hat, basically. And this is all salt water. And so the first time I saw a king tide, I was like, oh man, I'm not incorporating this in any of these inundation modeling efforts. It's pretty serious when you actually see it. And it gets crazy. So this is Miami. This is from September. And this is a king tide just a few months ago in Miami. This is a parking lot out front of a restaurant. And so that would be, imagine coming out after your shrimp po' boy and that's what you come out to. Maybe go back in for another cocktail, I guess, because that's pretty awful. And I like this one too. This is downtown Miami. Again, this is just September 29th. I like how this Toyota like pulls up to here and it's like, what do I do in this intersection? And then they just go, well, I guess I don't have a whole lot of choices. It's pretty bad. And this is all salt water. This is not a precipitation event. This is not a storm. This is not a storm surge. This is literally just a high tide. And so I started doing work with Climate Central to better put these together to figure out how many people are actually exposed to annual flood events in the US. And there's about 800,000 people that currently experience an annual flood event because of tidal flooding. And about 20 million people live in neighborhoods that are exposed to annual flooding as well. And this changes over time. This is with Climate Central. They wouldn't give me 6 feet. They only gave me 3 feet. And so with 3 feet, you're looking at about 45 million people who live in neighborhoods that flood on an annual basis. So this is 10 times more than what we would have with 3 feet of sea level rise, which is about 4.5 million. So this is a paper I'm working on it with Climate Central. This is trying to bridge together the different ways of categorizing how many people might be at risk when they do these sort of accounting schemes. And on some ends, you have as many as 1 billion people in the world that live in a coastal area, and on the other end, you have 180 million people who will live underneath the future high tide line. And so displacement is going to occur somewhere along that spectrum, where you have people who will never flood, who will probably migrate in anticipation. But then you also have people who will never migrate as well, who just simply won't move. And somewhere in between is where those numbers fall. So there are some things that we can do. The three main ones are protection, accommodation, and retreat. Protection is you build a seawall. Accommodations, you generally think of it as raising your elevation or driving through seawater. And then retreat is simple, moving people around. In the case of protection, it's real expensive. Coastal armoring is about $92 billion a year. It's the cost to maintain coastal armoring globally. And I think this is very conservative because California is $2 billion alone, let alone places like Egypt or the Netherlands or Indonesia and so on. So it's very expensive to build protection. Accommodation happens pretty frequently, but again, it's also very expensive. In the US, the cost to elevate a single-family home is about $194,000. But widespread accommodation seems a lot more likely than widespread protection. And people do this. This is one of my favorite Washington Post quotes in Norfolk, evidence of climate change is in the streets at high tide. And this quote from the Reverend Jennifer Slade, I don't know many churches that have to put the tide chart on their website so people know whether they can get to church, because it floods the parking lot and then they actually change their service schedule. So accommodation is relatively cheap in the case of changing your church service. It's very expensive in terms of elevating your home. And then retreat is also considered inevitable, but it's also very contentious and very expensive, right? So residents voice concerns over potential for managed retreat, or retreat not an option for California beach town, or Florida's Monroe County approves $10 million for home buyouts. So in terms of the three, retreat is very contentious and expensive at $200,000 a person. Accommodation is also very expensive for individuals, but it's easier to do. And protection is really expensive for institutions. So there are things you can do on the ground in these areas. I'm not sure how widespread adaptation is necessarily going to be. Places like New York can definitely afford it. Places like Hyde County, North Carolina, probably can't. And then I have some other stuff, but it's related. So to get to your question on the difference, right? So I have a paper coming out in June where we looked at Fukushima, what happened after the Fukushima nuclear accident. And in that case, the Japanese government actually has two different migration data sources. It was actually really nice. They have their permanent migration data, which is just traditional that they get from their population registry. But then they set up a separate evacuee system to capture people who were evacuating or displaced from the disaster. And they got like tax breaks and so on. There was very little double counting between the systems. So if you are in the evacuee system, you were not in the regular permanent migration system. So it allowed a very unique parsing to actually look at permanent versus evacuee migration in the event of an environmental event. And so we looked at the similarities between them. Oh yeah, so here's one, right? This is annual OD. It's very similar to what we have almost anywhere for OD, origin destination data. And the evacuee data was a completely different system. We only had evacuee data from Fukushima Prefecture as opposed to the broad, but we knew where people from Fukushima evacuated to all the other prefectures in Japan. And so we just used a statistical distance to measure this. This is a Hellinger distance, which is quite nice. It ranges from a 0 to 1, where 1 means that the distributions are identical, and or 0 is they're identical, 1 means they're exactly opposite. And so we can look at and calculate how similar all these different the probability distributions are for each different prefecture over time. And this is essentially what it looks like. These are Fukushima, Iwate, and Miyagi on the far left. They're almost entirely clustered around 0. The average is only about 3% difference for the Hellinger distance. The evacuees, on the other hand, are really different. Their Hellinger distance is about a 35% different. So the Fukushima migrants, the permanent migrants who entered the system as permanent migrants in the wake of the disaster, went to the exact same destinations in the exact same proportions before versus after, but the evacuees did not. The evacuees went to much more unpredictable, and their destinations were largely nearby, so very short distance. So Alan Finlay's got a really nice heuristic for understanding destinations for environmental migrants. And the second, he has 6 principles. And the second one is that most migration is short distance, which seems to be what evacuees do. And the other principles are largely around social capital and social networks, which is largely what it looks like permanent migrants do. So that's why I have more confidence in being able to say, you know, these networks, the destinations are something that is easier to predict, because this is exactly what we find. And I know the work in Bangladesh after tropical cyclones, they show the same thing. They can predict the migration after a cyclone to the destinations. The evacuees are the ones that they can't predict. Yeah.
And I was wondering what's going on with new settlements in coastal areas. You know, we were in North Carolina in the 90s, and we keep building and we keep expanding. And you know, you talk about these responses as what to do when the sea level rises. But what about even today? Do you have any even for your projections, it could be that the people living in coastal areas may be increasing. Is that the case? Do you have any insights on that?
yeah, I got a lot of pushback where people were saying that there's no way that coastal areas are going to keep growing into the future. And I mean, I would say no, the exact opposite. They continue to grow and they keep building in a lot of these high risky areas. And the literature on it is kind of spotty, where some of it suggests that the risk, because it gets riskier, it gets cheaper, which means that some other people that wouldn't be able to live in coastal communities now can afford it, and so you end up with different incentive structure for population growth in those areas. But that's the other nice thing, is that essentially by looking, by peering into the box, right, we can actually see the future and say, hey, that's not the future that we actually want. And so for some of this, they can actually aggressively zone to prevent population growth in some of the really poor areas and manage their growth better for different areas. So I know when talking with people when I was at UGA, Savannah was starting to do that, and so was some of the coastal Georgia areas. We're actually starting to proactively zone to say, hey, development that was going to go in here is now going to go in here because that's very risky and that's not. So in a lot of cases, it bends the curve, right? It changes the profile.
I have a quick question on the focus on housing values. They're presumably more forward than a house that is 50 years longer. My sense is like we're not going to stay there unexpectedly. So I guess my question is similar to that. How do you explain that disconnect on one hand, that is a thing that's not sustainable, that if you look at housing values, which are sort of the forward looking and you then see how that's my perspective. How do you explain that disconnect? Can't be related to the numbers that are out there.
Yeah, so they are impacting housing values. Yeah, and specifically in the neighborhoods where they have the king tide flooding, those houses are selling for 2 to 4% lower than a house across the street or in a nearby neighborhood. All controls. So the effect is already happening in housing values in some of these areas, and in some cases it's incentivizing migration to other parts, but in other ones people are now moving into those communities that couldn't afford those houses otherwise. So it's just not as widespread yet, because even with the king tide flooding, like in those videos, it's still isolated to small parts of Miami. I gave a talk at the University of Miami last year, and my cab driver asked me why I was talking, and I said, sea level rise. And she said, what's that? So, I mean, it's still, not quite always there.
Because, again, this is the casual experience in North Carolina. It's true that maybe between there's a difference, but housing values on the coast in North Carolina skyrocket.
Yeah, they're still going up.
And so I guess that the question that, and what supports that? Is it lack of regulation, or what's because they were ridiculous, just crazy.
Yeah, I don't know. I mean, because even gentrification is happening in parts of these areas where developers are going into, parts of Miami that are protected. They're at higher elevation, and they're, converting the houses, demolishing them, and putting up more expensive homes. So like it's like multifaceted. It's happening in a lot of different spots. But I don't know why just the home values continue to go up. Part of it's that it's not like immediate, right? It's into the future.
Presumably, after seeing your editorial, Hauer, a lot of people move following jobs. When you think about some of this future growth in Florida is really going to be foregone growth. Because if I were looking where to put my headquarters, and I saw
it's not going to be there.
I would not go to Miami today. So sooner or later, when this gets closer, when those kinds of king tides are covering bigger areas, and when the sea level rise is more apparent, employers are going to stop investing, presumably, areas where people are going to no longer want, they're going to retire in Sun City instead of Boca.
Yeah.
Or something like that.
Yeah, I would completely agree. Yeah.
So maybe you can also pitch this as like foregone growth as opposed to not all.
Oh, I see what you mean. Yeah. Yeah.
If you're trying to convince Florida to care about climate change, they're losing. Some of the people will literally pick up and move, but some just won't go there.
Yeah. Yeah. Well, I like that.
Getting more expensive, more visible debt. So to what extent, ultimately at some point, that would also begin to influence people
Yeah, and
Not like you can afford to insure yourself.
yeah, and flood insurance, it's probably a really great example of maladaptation because it also incentivized people to build into very risky areas that they wouldn't have built in without the flood insurance program. So we're
Isn't that changing now, that it's more difficult to get flood insurance in certain areas? I thought that it was all changed possible to get it. I think it's changing.
yeah.
I think that could incentivize people not to move here all the time.
Yeah.
I mean, those are public policy responsibility or private sector responsibility that should also.
But there's still 6 million homes right now, people that live in that area today, regardless of changes in incentive structure for future growth, right? So there's still 6 million people that live within 6 feet of elevation of sea level. Did you have?
No, I have the same question like Irma. The thing was, so responsible for harm, so I was looking at the response of the insurances.
Mm-hmm.
And I know that based on the literature that was published in the newspapers, past in Washington, plus there is a lot of Wisconsin, different from New York areas. And I'm just wondering if you have looked at this and tried to kind of get some more deeper insights on this.
Yeah, I mean, it's hard. I mean, some of that's really hard to disentangle, to pull it out. I did some work on what they have is the community rating system, which is one, the CRS credit. So essentially, if you have repetitive loss properties in a floodplain and you remove them, you're removing risk, and so the risk profile of the community goes down, and so insurance premiums should go down, and that was in Biggert Waters, which was one of the changes for insurance. We looked at that in Tybee Island, where there's the guy with the bin was going to put it out, and they couldn't use that mechanism. The return period for them for their investment from the city was like 350 years if they were to actually remove those properties. In order to, the savings that they would have paid back the money in 350 years. So they bailed on that strategy. So some of it's hard to do, and some of this, the adaptation planning relies on what local governments are actually going to do, which is extremely unpredictable. So it's a messy problem.
So just a step back from it. So we don't know what's going to happen with flood insurance, and I think we talked yesterday about how in many cases flood insurance does not protect lower income households. There's another way to reproduce inequality, but I think if we step back and look at an aggregate of what you're saying, just from king tides and sea level rise, projected 45 million Americans, right, living in areas that will flood at least once a year. And so it could be that with some preemptive adaptation, that number would come down. Okay, so it's a large number. We could add another thing like extreme heat, like in the Gulf Coast, it's like, or Phoenix, Arizona, half the year at least, but not 5 degrees Fahrenheit or something like that. Extreme fire risk in California already 2 million of fire risk, another 2 million around the country, more or less. So it seems like one way of just understanding what you're saying is like net of any particular detail, the pressure for migration is going to be absolutely massive. And a lot of that is going to fall on people of color, and a lot of that is going to fall on older people, and lower income people, and none of whom are like really beautifully equipped. So let's say change cities. And so that there are different things that flood insurance might do to change that, but no matter what, this is just an insanely large change coming down the pipe, for which clearly nobody is ready. I mean, does that seem like a fair?
Yeah, but they're getting more ready, but still behind the 8 ball. Yeah. 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 I have not, no. No, I haven't. That's a great question, though. Yeah, well, that's not a bad idea. It's good affordable housing too. So you get a twofer. Yeah.
Matt, I wonder if you could talk a little bit about kind of like threshold effects here, right? Because one of the reasons people keep moving to denser, even suburban or rural communities, especially in Texas and Florida where there's no income tax, is that the entire municipal and state budget is floated by property taxes. And industry is not pulling out because if you're on the investment side of real estate, you're only in a project at the most for like 7 years.
so after 7 years, you really like not care at all what happens to that place. So I wonder if you thought through, outside of like projecting a linear curve or exponential curve, some of the big cultures or thresholds would be in which, what I think your number, like the 45 million number, being like the most conservative possible estimate for how many people will be displaced. So if you think about like what the threshold would be at which like those big pulses of migration happen, and then how many more people, given that like municipal and state budgets would collapse in places like Texas, Florida, might also be displaced.
So Louisiana is a great example for this, because Louisiana has a physical hazard that mimics sea level rise pretty strongly. They have coastal subsidence, so their land area is sinking. So if you look at Louisiana, the boot doesn't look like that, right? Like that's the classic example. It's washing away. And since 1924, Louisiana has lost about a third of its coastal land area as it just sort of subsides away. And part of it is sea level rise, part of it's storms, part of it's just land management strategies that are really poor, part of it's oil, natural gas pipelining. It's a perfect example of a coupled system between them. So I don't care that it's coupled or not coupled. I just care that it has a physical hazard that mimics sea level rise and that it's a conversion of land, and it's over a time horizon that's very similar to what we would experience under sea level rise. And it's pretty big. It's coastal Louisiana right now is about at 1.3 million people. And when you look at the other examples of sea level rise historically, they're all small islands. The largest, I think, was in the Chesapeake, and it had about 180 people in it. So you're looking at really tiny populations that are islands, hard to generalize from the really small end to a broader mainland community. And Louisiana is a great case example where you have a mainland community that's pretty large, that's experienced a physical hazard similar to sea level rise over the same time period. And so I standardized the block group boundaries back to 1940, so I ended up with a long time range of population, and I could look at which block groups were undergoing population decline based on how much they had subsided. So how much was their land area gone, and when did they actually experience population decline, or did they? And for the average block group that had subsided in Louisiana or experienced any form of subsidence, about 1/3 were in decline, and so 2/3 were still growing in spite of their actual subsidence. So the sea level rise hazard did not overwhelm their ability to continue to grow, because it could just be 1% of the neighborhoods underwater, which is like not a big deal. But when about 50% of the neighborhood was underwater, all of those ones were in decline, and it was a very small number of block groups that were like that, but they were finally going down. So these are assuming that you're underwater all the time. These numbers are, but it might be impermanent not quite permanent inundation that actually drives population change. And so the threshold is much sooner than 100%. It could be 50%. It could be 5%. So for a lot of communities, they'll see these front end effects much sooner than 2100 for one thing, and it's much worse when you factor in both intermittent tidal flooding into it, which is the king tides. You end up with upwards of 45 million people that are experiencing some form of an event, which is causing property damage, reducing property values, enhancing commuting times, and so on. So the thing that I'm really worried about for some of these areas, if they don't start being very proactive now, is that they essentially can't catch up. So as king tides start eroding away their property values, their property base, their tax base starts dwindling, and that's how they're going to be able to pay for all their adaptation. And if they can't pay for their adaptation, then their property values continue to erode, and you end up with this downward spiral.
Yeah, I mean, this is to monopolize one last question. This is kind of what I'm wondering if you're digging into in Texas and Florida specifically, where City of Miami, Miami-Dade County have to incentivize real estate development. They'll just provide basic services and keep their debt obligations.
Yeah, the perpetual growth machine.
Yeah, there's no other way for them to float the budget without that incentive structure in place. And so I'm wondering if you've started to model, or other folks are modeling sort of municipal or state debt obligations and the effect that losing even 15-20% of their property taxes would have.
Yeah, no, I haven't. When I was at Georgia the last semester I was there, a budget professor approached me to look at state budget finances and climate change and migration, and the project didn't really go anywhere. But she was really interested in trying to figure that out. We'll get to that, but it was state level as opposed to local. Yeah, I mean, I think that's really at the forefront, because if you can't adapt to this stuff, then it gets worse, and then the incentives to stay goes away, and so you end up with this downward spiral. But yeah, I haven't looked at that. I don't know a lot of people that are.
On the note of this downward spiral that we're all facing. Thank you so much for that.
Thank you.